And as you saw in the talk of the linear optics, what we calculate usually is this first coefficient here, that's the linear response. But solving this time-dependent nonlinear, this time-dependent Schrödinger equation is possible also to have access to other coefficients of the nonlinear response. Here there is a typical example of a nonlinear phenomenon where you send red light on a crystal and you measure the response in green. So the schematic representation is this one. We send the red photon and you get the green one. Typical application was the green laser, even if this slide is a bit outdated because now there is a directly green laser, but the first green laser were expensive because it was a red laser, then it was changed in green with a nonlinear crystal. I will skip all this example, and I want to just tell you an idea how the code works. So what we do in fact is in the code we write an equation for each valence band. We propagate in time in presence of an external field, and then similar to what is done for molecules. This is an example taken by TDFT for molecules. For example, you put a perturbation like this, you get some oscillation that are the linear response oscillation, but then you get some oscillation at 2 times the frequency that are very small. You don't see here, but they are in this line. And this is the nonlinear coefficient. And thanks to the tool that is included in the post-processing part of Yambo, you can extract this nonlinear coefficient. This part of the code has been tested on bulk material, but also 2-dimensional materials, both for second harmonic and third harmonic. I will not enter in the discussion of the Berry phase because it's rather complicated, but just to say that there is a particular way to describe the coupling with the external field. So the code in principle takes all the information from the FT as you have shown for the other calculation. You include an external field and then you propagate in time, you get the polarization, and from the analysis of the polarization you get the response. You can include all correlation effects that we have seen for linear optics, so you can correct the band using GW, also in nonlinear response, include local field effect, and include also electron interaction, and they will enter like TDR3 or TD exchange. And let's see if there is some example. So these are typical a result of real-time simulation. You get the polarization in time. So these you evolve for a certain time. Then by Fourier transform, you can get your optical absorption, for example. And according to the level of the theory that you put in real time, you get an absorption in Fourier space that in frequency space that respect this level of theory. For example, here we did a simulation in TDR3, and you get the electron constant in TDR3 that clearly was far from the experiment at this gray. But if you do a TDBSC, that is, I say, anyway, it's quite expensive, what you get is really a beautiful exciton, like in this example here. This was for linear response. The same can be done for non-linear response. These are some example of second harmonic generation in bulk semiconductors. The dot are our calculation and the line are calculation from other groups. So just check to see that the code works. And these are the experiment, for example. And you can also do the calculation at different level of theory. This, is, for example, is the nonlinear response of molybdenum disulfide at the independent particle level using TDR3 and including TDR3 plus screened exchange. And this is the experiment, is the black. So it was not bad. And as a final example, 2-photon absorption is another phenomenon, but it's quite complicated to get, so I will skip it, and I will show you the example of third harmonic generation, and this is also a tutorial on this part. So there is this is the third harmonic coefficient. So it means you excite at omega and you measure the response at 3 omega. And this is a typical example for silicon. Now, the code is working. Calculations are not easy, at least at level independent particle. Everything is feasible, probably also in 3D artery. Inclusion of exotonic effect can be quite expensive. For solids, I think is more or less not impossible, but close, because it's very difficult. But if you have a 2D material or a material that converges very fast with K-point, this can be probably is possible. So on the wiki, you will find on wiki tutorials, nonlinear, a number of tutorials. So how to get a linear response, how to include correlation effect, how to calculate third harmonic generation, and also how to include spin orbit. That is already included in also in nonlinear response, even if I think we never used it. In the typical tutorial, what you start from a DFT calculation. You have to remove the symmetries, because when you are in real time, you apply an external field, so your full Hamiltonian will have less symmetry than the one at the equilibrium. So there is a tool to remove the symmetries. But you can find everything explained in the prerequisite for real time. It explains how to reduce the symmetry, how to get prepare the wave function. Then there is a simple command that is Yambo NL minus U. You have to, sorry, I forgot. You have to compile the nonlinear version of Yambo that will do the same things on the linear one plus the nonlinear response. You have to choose an interval of energy where you want to calculate the nonlinear response, a number of steps in this interval of energy, a damping factor for the nonlinear response as you choose for the linear one, and the direction of the external field. So you simulate to get something like this, where this large oscillation at the linear response and the small oscillation at the nonlinear. Then in YPP, there is a tool to analyze the response. The polarization is approximated with a many oscillation term, and then this tool extracts the different coefficient, and you get the nice spectra that you see here. That is the nonlinear response, in this case, the aluminum arsenide, and compare it with other calculation, and with converged K-point, and so on. Some care has to be taken to choose the direction. We recently updated also the tutorial to explain how to choose the direction of the field, because, for example, the Chi2, that's the second harmonic generation coefficient, it has 3 indexes. Is Chi2 A, B, C, because there are 2 incoming field and 1 that is outgoing field. The field that is in the input determine the incoming field A and B, and then the analysis of the response give you the third, the missing field. So these are, for example, all the possible combinations. If you put the field in C direction, you can calculate Chi2, Chi2, and then all the response of the other direction. If you put in Y direction, you calculate the Chi2, YY, and the other direction, and so on. This gives access to all this direction. What say? In the file, there are different columns that correspond to the different real imaginary part of the different direction. Here I see that there is an error. I will fix. Okay, yeah, that's more or less. Yeah, for sure there is much more to say about nonlinear response. What is the nonlinear coefficient? But this.
Yeah, I think that if I can.
Yeah, you can.
So an important point with respect to the response-based that we have seen is that we have a field which is a physical field. So in what we have seen yesterday with Bede-Salpeter, or also in the first day, we had some perturbation, and then this perturbation is actually a mathematical perturbation that it's used to get the response. In this case, we have a real field, so we have to, if we specify a direction, then you see that we have to consider the system plus the direction, and therefore the symmetry of the whole things. This does not happen in the response because basically your perturbation is a mathematical perturbation, goes to 0 at the end. So it's not really, it's perturbing the system, but it's not physically interacting with the system, I would say. This scheme, which is real time, it's much more similar to a real experiment. So, for example, Claudio showed the linear response at the start. This was just created with a small delta kick. Instead, if you want to have for the second harmonic or a third harmonic generation, you will send monochromatic waves, and then you have to swipe over all the frequency, for example, and then how you get one response or the other is also depending on what you are doing in post-processing. So it's really like, I mean, you can really think about an experiment. So theoretically, you are just you have your system with your Hamiltonian, which is the level that you want to treat. And then you just input the field, and then you have to do something in the output with the polarization in order to get the response you want. So in this sense, it's also much more flexible than the other code, because you can change just what is your field in input and your post-processing tool, and then get different responses. So this was what I want to add.